So when we talk about the light from a star, there's another thing we can talk about, and that is what we call the Doppler effect. Now, the Doppler effect was actually named after a fellow named Christian Doppler, who was studying sound waves. And he noticed that, for example, something going past you would change sound. So, for example, a car driving past you, okay. It's not that the car is shifting as it goes past you. What's happening is that it's giving off sound waves, but if it's coming towards you, each of these sound waves starts closer to you than the other one, and so the spacing between them is less. And as you're going away from you, each one starts further away from you, and so the spacing is farther away. And so what happens is that since there's a relationship between wavelength and frequency, a shorter wavelength makes a higher frequency, and a longer wavelength makes a lower frequency. So this became known as the Doppler effect, after Christian Doppler, who described this thing. And it was for sound waves. And so he's describing sound waves when he does this. And so a lot of research was done as to how this Doppler effect relates to sound waves. But light is also a wave. And so astronomers began to realize, and physicists began to realize, that this is also an effect with any kind of wave. So if a star is coming towards you, then the waves look shorter. If it's going away from you, the waves look longer. So that means if you were looking at a star that's coming towards you, and you have all these spectral lines, the spectral lines would be shifted to shorter wavelength, or if it's going away from you, the spectral lines are shifted to longer wavelength. How far the spectral lines shift depends on how fast you're going. Okay, so if it's shifted towards the red end of the spectrum, we call that red shifted. If it's shifted towards the blue end of the spectrum, we call that blue shifted. Very, very unoriginal. Okay, now technically the blue end of the spectrum is violet, but we still call it blue shifted instead of violet shifted. So blue shifted means it's coming towards you, because that means shorter wavelength. Red is longer wavelength, so red shifted means going away from you. So you could actually figure out how fast it's coming towards you or going away from you. There's a formula for that called the Doppler Formula. And so, for example, let's say that there's a star that you know the wavelength, so lambda sub 0 means the wavelength of what that star is going to be if it's not moving. So there's a particular spectral line. And let's say that you know that spectral line is going to be equal to 467.23 nanometers, but you measure it to be a little bit different, 467.26 nanometers. So it's shifted a little bit, and you want to know how much did it shift. The difference, this where it says delta up here, that means difference. The difference is 0.03 nanometers. And so we can find out how fast it's going by saying that's equal to the difference, 0.03 nanometers, divided by the lambda sub 0 means that's what it's supposed to be, 467.23 nanometers, times the speed of light. Okay, speed of light is 300,000 kilometers per second. And so we could then find out that shift, 0.03 divided by 467.23 times 300,000, that turns out to be 19.3 meters per second. So we can now find out how fast something is going by this shift of the waves. Well, it doesn't even have to give off waves. What could happen is you could have a wave going along, bouncing off of it, and so it bounces off shifting. That's the idea of how radar works. And so the police can bounce radar off your car, and it comes back Doppler shifted. The bigger the Doppler shift, the faster you're going. So if you get too big of a Doppler shift, they stop you and chat with you about that. Okay. And so that's the idea of how this works. Now, the interesting thing, the middle bottom here, the state troopers, they actually use a laser instead of radar, and it's more precise. They can pick one car out of a whole bunch in traffic, versus radar, which mainly is good for just isolated vehicles. But the Doppler effect is used here, but we can also do this in space. We can bounce radar off of a planet and measure the shift, or even a star. We can look at the Doppler shift of a star and find out how much the light is shifted from the star. For example, if a star's rotating, the spectral lines, instead of being one wavelength, some of the spectral lines are shifted towards the blue, some are towards red. So you look at the spectral lines, they tell you what makes up a star, but the fatter the spectral lines are, the faster the star's rotating. So that means by looking at how fat the spectral lines are, we can figure out how fast the star's rotating. So not only can you figure out what the star is made out of by the spectral lines, you can also figure out how much it's rotating. We can also figure out by the fattening of the star lines how much turbulence is in the star, because different parts of it are moving differently. And in fact, if the electrons bump into each other, that also changes the width of the spectral lines. So small stars have fatter spectral lines than big stars, because the atoms bump into each other more. And so by looking at the spectrum of a star, by looking at the peak wavelength of the star, so the peak wavelength, the color is most intense coming out of the star, that would tell you the temperature of the star. So that is the blackbody radiation. By looking at which spectral lines you have in the star, that tells you the chemical composition of a star. Okay. By looking at the shift of all the spectral lines, that tells you how fast the star is coming towards you or away from you. And the width of the spectral lines would tell you something about the rotation of the star. And how those spectral lines are adjusted here a little bit tells you the turbulence or pressure in the star. And so all these sort of things, these are things you can figure out about a star without actually going to the star, just by looking at the spectrum of the star. So just looking at the light of the star. So this is the power of all this. This is the power behind it. This is how all this works, and this is why we study light. So the nature of studying light from a star allows us to figure out all of these effects of a star. And so that's a very, very powerful tool right there. And it's kind of interesting how that works. And so you can also use this on Earth. You can look at the spectral characteristics of something and figure out what it's made out of. So they do this, for example, with crime scene investigations. They find this weird little substance. They know what it is. So they do spectral analysis of it, find out what it's made out of. So there's all kind of applications of this outside of just astronomy. And it gives you kind of an idea of the science behind it all. And this is what we have to do with astronomy, because, as I said, we don't actually get to go to the star and make the measurements up close. We have to make the measurements from very far away. And so looking at the light tells us about it. The peak wavelength, that's the black body radiation that tells you the temperature of it. The spectral lines tell you the chemical composition. So this is the peak wavelength, is the temperature. The spectral lines tell you the chemical composition, and the radial velocity of the star, that's the shift in the spectral lines. So, and then the width of the spectral lines tell you these other sort of factors down here. So we have like I said, the temperature is going to be the peak spectral line. The shift in the spectral line tells you how fast the stars are moving, which spectral lines you have, chemical composition. So all of this there's a lot of stuff you're able to figure out about a star just by looking at the spectrum. So this is what astronomers will often do. If they see an object, they don't know what it is, they use a spectrometer. They break the light out into all the different wavelengths of light, and they study that, and that tells you all this stuff about the star.